Cool. All right. Thanks a lot to Martin for that talk. It's fascinating. Slightly different approach, I guess. Look, like from that very sort of broad global perspective, I'm going to zoom into kind of creating software systems. Although still looking at kind of distributed nature, I suppose, to some parallels. But yeah. Okay. So I'm Matt. I head up the R&D working group at Energized Work. I'm going to talk to you about a few things. First off, I'm going to have a review of some sort of modern architectures that we use to build software systems, particularly websites. I'm going to introduce you to Elixir, Beam, and the OTP, and do a review of that technology stack and see if it solves some of the problems that I'm going to present. And then look at evolving distributed systems. So the title of the talk was Building Monoliths from Lego, and then looking at how we can evolve distributed systems. So let's start with reviewing these architectures. Okay, so before I even ask this, who in the room is a programmer? Okay, just to get us a bit of a spread before. All right then, so who works in distributed systems?
Define distributed systems.
Yeah. I'm about to. Yeah, so all right, that's interesting. All right. So my answer to that is anybody working in the web. Controversial or not? I don't know. There was I didn't think that was, but okay, let's see. Yeah. So the definition, or a textbook definition of a distributed system is co-located network components that communicate via passing messages to each other. There's a concurrency in the system, no global clock, and there's ability to deal with independent failures. So I think in reviewing the way that we build a lot of web architectures, some of this will kind of start to gel a little bit more. So a very common simplistic, or the most simplistic pattern is a kind of monolith, right? So where we have all the different components that we need, user interface, business logic, application, everything in one unit. Simple to build, or the simplest to build. So we have this kind of setup where the browser's talking to the app and the app talks to the DB. But then we quite quickly get to the point where we need to do something that doesn't fit very well in a quick request and response cycle. So we start offloading work to message queues, and then we need something that's going to process the work that's on that queue. So it's simple, but quite quickly we get to the point where we need other distributed components. And I think one of the points I guess they're making is that often these worker components are not local processes, right? They tend to be something else that's spun up. So it could be inside Docker or some other runtime, or it's another machine that does the job of a task. I didn't start my clock, so I can't see. Okay. All right, so you've got this kind of flow, I guess, fairly standard stuff, I guess, to a lot of people that are coders in the room. But so we have this request and response. But because we're going to schedule some work and we're going to do some background work to do the RSS fetching in this case, so it could be something much more simple like fire and forget, like sending an email, right? We don't care about the response from that. But in this case, we're talking about something that we do care about the response from, right? So that's one pattern. Another one that comes up a lot at the moment, microservices, right? So this is another way to very consciously build distributed systems. So for anyone that's been around long enough, it's an evolution of things that we've done in the past, SOA. I guess it's it's kind of lighter weight protocols. That's the key takeaway. The size of the things is impossible to define. I stole this picture from Nginx, who are busy punting their product at the minute as a gateway for microservice architectures. But you can see the point is there's a lot of collaborating components, much smaller in size, that are required to achieve particular tasks, and cross-dependencies between them. So I think with this kind of setup, it's worth looking at what's good about it and what's not so good about it. And so I think the advantages are fairly clear. I mean, this decomposition, this kind of Unix philosophy, do one thing, do it well. Having good boundaries in the system. Public interface, private implementation, again, very common pattern in computer science. Independent development, deployment. and elasticity of the particular services as well. Scale them up if you need more of them, throw more resources at it. Disadvantages, there's quite a lot, I think, anyway. You need to think about the network interface that you're going to communicate over. So quite often REST, but it doesn't have to be, could be RPC. Orchestrate the different infrastructure that you're using. Scale it up, scale it down, create servers for it. And this, to me, really lends itself to being a heavyweight process, right? Like, often these things are not doing a particular amount of stuff. They might be doing the same thing over and over again. They might have a lot of throughput, but not doing a lot. But we weight a lot of infrastructure around them to let them do their job. Difficult parts, obviously, distributed transactions, eventual consistency. It's hard if you can't do everything in the same transaction in a database, right? That's how it is. There's a development in QA overhead. Working on this stuff takes longer. Pull lots of projects together and fire them up locally to get them to talk to each other to test, get them to do what you want. QA is even harder. Service resilience, well, you have to build something like that, or yeah, and then monitoring and versioning. I think that's fairly clear. All right, so probably fairly famous, this slide. But, so it's what Martin Fowler calls the microservice premium. So you've got complexity going on the x-axis and productivity on the y. And the point being that for less complex systems, there's a lot more baggage to create and manage microservices at the start point, right? And then as you move up the complexity, you eventually get to a point where the benefit of microservices pays off, right? So we're having this distributed system with all these kind of good properties that we recognize from a distributed system. Makes sense. Obviously, the great thing about graphs is that there's no numbers on here, right? You can't define complexity in like units, but yeah, you get the point, right? There is some trade-off, there's some balance, and at some point they're beneficial, and at some point before that, arguably they're not. But they're very popular still. So that led him to say this: don't use them unless you have to. Furthermore, yeah, majority of systems don't need them. Build them as a monolith first. So controversial, right? Even people within ThoughtWorks, the company that he works for, don't agree. But anyway, it's a view that's out there. So maybe a lot of you are thinking, kind of what? Because I mean, we have this is a very common pattern in places that we work. And so I think we just have to kind of recognize, what we're building here that is a distributed system, and look at the properties that requires, and try and figure out the best way to do it from zooming out a little bit. But for fun, first, let's go back in time a little bit. So this is definitely cheating, because this is not a modern architecture. But this is a trading and settlement system I worked on back in 2000. So it's a single Unix box with a bunch of daemons written in C, a scheduler that orchestrates them. Events come in from desktop interactions, booking a trade or making a settlement. That kicks off the scheduler, and it flows through the system. Work happens, right? I guess the point is that it was a single box. It worked. It dealt with a ton of throughput. It was an old Unix machine by today's standards. It's global shared state in the database, but share nothing architecture amongst the workers or processes themselves. So it's concurrent, and the processes ran in parallel, or the workers ran in parallel. Yeah, and most importantly, obviously, I talk about old systems in C just so you think that I'm properly legit, because that has to be looking. Yeah. All right. So that's our kind of review of where we're at, and I want to talk to you about some potential solutions to this. What things I see as problems anyway. So Elixir, Beam, and OTP. All right. So you can't talk about Elixir without talking about Erlang. To my slides. Yeah. So functional language created in the 80s. So a long time ago. Telco systems at Ericsson. Erlang runs in Beam, which is a virtual machine. And Beam manages a lot of lightweight processes that collaborate with each other, no shared state. And concurrency is a first-class citizen in the ecosystem. It's like approach similar to the actor model, if anybody knows about that. But we'll talk a bit more about that as we go. So whilst I talk about all this distributed stuff as well, like it doesn't have to be distributed. It's going to run on a single node, on a single box, but the processes can still communicate in the same way. Remember that date as well. I mean, that's predating Linux and the JVM, right? So this stuff's been around for a while. So OTP is a component of this ecosystem, which is standard library on steroids for a lot of situations. Open telecom platform, sort of badly named, so it does a lot more than work in telecom systems. But yeah. So you've got a few things. There's a distributed in-memory key value store, so equivalent of a distributed Redis or something like that, if you've used any of those kind of tools. A distributed database as well. This is all in the box, right? So as soon as you fire up the ecosystem, you get these things. There's the process supervision that I talked about, and some common abstractions for like dealing with processes as well. So GenServer is one of those, which is an abstraction of kind of creating and running a process to do a piece of work. It's very simple. So then we roll into Elixir, right? So that's the Beam gateway drug, right? So yeah, that came out in 2012 by Jose Valim, who was a prolific Ruby guy. Trying to nail the concurrency problem, I think, in Ruby and deciding not to, which is probably quite smart. So dynamic functional language. Leverages Beam, it compiles to bytecode, and it's got full Erlang interop. So you're standing on the shoulders of all of that tech. It's been around for a long time. So yeah, why do you care, basically? Well, going back to my original point, I think that like if we recognise the systems that we build as being distributed systems, then we should use a tech toolkit that is sympathetic to the types of systems that we're building. And just to reiterate that point, that so the work that those processes do can be distributed across a single node, across multiple nodes, and then across multiple machines. So a node or a VM can run on a single machine, and multiple nodes can run also on a single machine, but then you can scale those out if you need to. So there's a few factors that help us to kind of achieve these goals, I guess. So the fact that Elixir is functional, it has a certain properties that mean that concurrency becomes a lot easier, right? So it's immutable. There's no shared state. I'll come back to that. It operates through transformations, so everything is data in, data out. Similar way to Unix pipes, I guess. It's idempotent, so same input, same output, always. It never changes, nothing will change underneath you. Pattern matching and destructuring, method matching, that's just a kind of idiom of the language, but it makes it very nice to work with. It also makes testing a lot easier as well. Getting into Beam itself, and the important part really, which I think is this process architecture. So like I said before, it's similar to the actor model. Arguably, it's hard actually to decipher from internet conversations, but it seems like they kind of evolved in parallel. But there's a lot of similarities. So these processes are very lightweight. They're easy to create and destroy. Right? There's very little overhead in doing that. They're isolated. They only communicate through message passing, so they're quite safe to use in that sense. Processes can be supervised, and supervisors are processes, so yeah, you get a tree of processes that can look after each other. They're composed into applications, which are a bit like executable libraries or services in other parlance. And then they can communicate across nodes by default. Right? What did I say? Okay, right, so yeah, I was going to show you a little bit what that looks like, but I'll do it via a real world project, right? So sort of digressing a little bit, but hopefully for the worth of it, and apologies to the Energized Work people because you've seen a lot of this already. But, so the Monolith so we got to Monoliths eventually, right? It took a while, but this is not a Lego one. This is a public art project made by a friend of mine in Slovenia. It's environmentally aware, it's got some technology inside it. It takes pictures of the sky and analyzes them based upon a blueness scale invented in the 18th century. It's also got some environmental smarts. It does reports air pollution and air quality and that kind of stuff. There's one in Ljubljana at the moment and one in Wrocław. Marcin?
Yeah, very well. Definitely better than the first time.
Thank you so much. So we've been doing it every day. All right, so yeah, the point of mentioning this really is to look at how it's been architected, right? So the monolith itself pumps the images and various other bits of information into the Cynometer application that I've created on the web. So it's got an API, usual kind of stuff. And then there's a web user interface and an archive user interface that deals and communicates with that. And so the first one of these we did, it was fine, right? I needed to get some information from an external weather station or measurement station, right, to get the pollution levels that we display on the website. And so I just had my JavaScripty stuff in the page go off and get it and display it, and it was all good. And then the second one came along, right? And then, of course, you've got a problem, right? Because you can't use a similar approach for this misshaped data and all that sort of stuff. So I needed some way of kind of abstracting that and presenting it to my application so that I could use it in a sensible way. So that's a very long way of me saying that I came up with this separate application, the measurements application and the Cynometer application. And what we can do, hopefully, let's have a look. So I just started up the application, which was the web API and also the measurements application together. And what I've just run, observer.start fires up this thing, which is the kind of inspector for the Beam runtime. Right, so it's a bit like your Process Explorer if you're looking at your operating system. So maybe, yeah, there's quite a lot in here, but the two important things are we can see, I can't see it, where is it? Cynometer's there, right? That's one application. Measurements is down there somewhere as well, down the bottom. Can I make that bigger? Actually, I could probably do that. E. It's hard, isn't it, when you're doing it backwards? All right, so there's a kind of supervisor process here, and if we look down the tree, it has got an endpoint which deals HTTP, and then further down the other side, it's got a repo that talks to databases, right? This stuff isn't really important, but the point is that there's this process hierarchy that you can follow through, and you can click on these things and get information about what they're doing and what they're up to and that kind of stuff. Of course, if you drag it across to the right window, you can. So back on point a little bit, I talked about the measurements thing and the need for having it. We can actually sniff around inside this measurements, yeah, of course, process and see what it's doing. So there's a whole bunch of information, you know, like at the system level we looked at what memory is being used and all that kind of stuff, and we can trace data through it. But really the simple thing I wanted to show you is it's got a state that you can inspect, right? So I don't know how well you can read that, but anyway, it basically says Ljubljana, then it's got a bunch of readings for nitrogen, sulfite, ozone, etc., and the same for the other place, which I'm not going to pronounce again. So we were able to very easily spin up a lightweight process that communicated with external APIs, held some state, and then made it available to our web application. Okay. Where's my mouse gone? So back to looking at the advantages of the platform. So that was sort of diving into the processes and sort of saying why I think they're useful and giving you a concrete example of how I've used them before. Sort of last feature of Beam really, and this is not particularly controversial, but it's got its own scheduler inside it, and the scheduler takes care of managing all the processes. I should say that that's completely separate to your operating system processes, right? So there's only one operating system process that runs, which is the Beam itself, and all the other processes that you see are inside the Beam, right? But it uses preemptive scheduling to deal with that, and long and short of that is that you're not going to get a process that chews up your computer and makes it grind to a halt. So if you see, it context switches between the two processes, allowing them equal time on the left-hand side, and on the right-hand side you've got one halfway down in the middle that takes a long time. So something like Node.js, for example, has cooperative scheduling, which means that a long-running process will kill your box. Right? Learn that lesson. Anything that just comes to a halt or takes a long time, bring your system down. All right. So you can't talk about Elixir without talking about WhatsApp, and numbers, whatever. But that is quite interesting, right? So in 2011, they got 1 million TCP sessions on a single machine. It's quite impressive, right? 100 gig of memory, 24 logical CPUs. 2014, Facebook paid 19 billion for them. Yeah, 450 million users, 32 engineers, right? That's pretty low, right? Got more than 70 million LM messages a second, hundreds of nodes. By this point, they'd scaled right out, lots of cores, lots of machines. So they'd gone from a single box, right out, and built with a lot of throughput. And obviously, I'm talking about it because it was all built on Erlang. So that's the obligatory side. Okay. So can we use this stuff instead of microservices? Is it a valid replacement? Well, I guess we can go back and review the things that we said were good and bad about them in the first place and swap in Elixir and see how that works. I don't think there's anything controversial on the left. I mean, to me, all of those things are fairly clear still, the way that we've described them. So we get all of that. In terms of the disadvantages, well, you don't have to think about the network interface, so that's not a problem. Orchestration, yeah, well, not at the same level that you've got to deal when you've got individual different bits of software needing to be deployed. Obviously, you still need to, if you scale out across multiple machines, you still need to manage those, but you don't necessarily need to start from that point. So that's why it's 50-50. So the processes are very light. They're not a computer or a container. It's a process, right? Distributed transactions, eventual consistency. Go figure. That's hard. Nothing's going to solve that for you. The development and the QA overhead goes away. Certainly in the early days. They're resilient because they're supervised, and the monitoring comes out the box. I showed you that. Versioning, well, again, early days, not a problem. Later, maybe, if you scale out. So yeah, I guess the point I'm really making with this is that we talked about recognizing the types of systems that we've got and looking at some of the tooling that we use to build these. I don't necessarily think is the most efficient choice. So my kind of argument is that if we start from something that's got the right concurrency primitives built in from the start, it gives us the things that we need. It gives us the way to manage these processes, and it gives us options later on, right? But it's not a silver bullet, right? There's no such thing. It's just another option in the options that are out there. How long have I been? Is this 20 minutes or something? Okay, I'm going to rush through these because there's a bit more. All right. So I'm just sort of making it easy for Thor to come in and steal the glory anyway. It's all Oh, Christ. All right. I can talk in a lot of detail about the fallacies of distributed computing if you want. You will all fall asleep. Anyway, I mean, look, I don't think this is going to be, news to anyone really. So networks aren't always reliable, right? Things go wrong, power goes, things blow up. There is latency, bandwidth isn't infinite. Security is always a problem. So I'm kind of shooting myself down a bit here, but these are not factors that are distinct to Elixir or Erlang. These are factors that are distinct to distributed systems if you go that way, and that's what we're building half the time. So you have to think about it in those senses. The fact there's more than one person that looks after them. There is a cost in moving messages around and serialization, and they don't always talk the same protocols, right? So back to the title of the talk. So how do we evolve these types of systems? Well, there's a few strategies that we can use. Yeah, so we don't have to pay that kind of cost up front, right? So we can start with an architecture that gives us escape hatches for later. There's a concept of an umbrella application in Elixir. So Mix is just a sort of utility or provisioning tool that you can use. So you can see in this instance that we create this kind of umbrella application, the overarching thing called a bank platform, and it's got a few sub-components or services, if you like. Authorization, some web interface, and some messaging component. This is an example that someone's built on GitHub that you can follow if you want. So if you look, it's underneath the application directory, and there's these separate components here. And I mean, it does a fairly good job, right, of explaining what the system's about. You can get some reasoning from it. So that's great. So at that point, we're still talking about one repo, one server that it's deployed on, a bunch of components that kind of communicate within that server. But then what happens if we do get to that point where we say, okay, well, this messaging component is just not open, it needs its own box. We then need to look at breaking it out. And so this is just a short example of kind of giving you a flavor of what it feels like to sort of take a module that you've written to work with locally and then pull it apart to a different machine. So IEX is an interactive session, just a command line tool. And it basically will fire up a virtual machine, right? So in this case, we're firing one up called auth at a particular host name, right? And within the web application, we then need to say, well, look, where does this thing live? So we need to kind of connect to it, right? So there's a bit of configuration that says, well, we've got this other service living on some host name, and I want to communicate with a module in there called myapp.auth, right? That'll become a bit clearer. So inside the web application that's going to use this other distributed node, we firstly have to connect to it. So that's what that first chunk of code does. It just says, get all of that bit of configuration, find all the other nodes, and connect to them. And the second bit's really the important bit. So the first line, which is the, can I do the local? Oh, I should have been using this, shouldn't I? Hey, this one. So the local thing is what it looked like before we moved it out into a different node. Just a method, right? Just a module with a method call. And then we can start to see what it looks like if we need to distribute it. So these are the kind of changes that you need to think about, right? There's a bit more to it than that, but let's keep it straightforward. Like whether you care about when the response happens, whether it's synchronous or what happens in the meantime. But it's not too much to change things. Okay. So just to review it and wrap it up. So we reviewed what I think modern web apps look like and recognize that we're talking about distributed systems. We appraise the benefits of them, the architectures that we use, and look at the costs as well. I introduced Elixir, OTP, and the fact that it's got this concurrency and parallel distributed nature to it, all as first-class components. I then showed you how we could use umbrella applications to define these kind of boundaries and give us this, escape hatch to see what happens when we decide we need more resources under the covers and scale out to multiple servers. That's it. Thank you.